Welcome back, everyone. We're diving into the world of elements today, and this one, well, it's a bit of a phantom, you could say.
A phantom element. Sounds intriguing.
Oh, it is. We're talking about francium.
Francium, huh? Okay, I'm listening.
You sent us those Wikipedia articles, and it's clear that francium is not exactly hanging out on every street corner, right? It's like one of the rarest elements out there.
Rare, you say?
Rare, like less than an ounce of it exists on Earth at any given moment.
Wow, that's pretty scarce. So, where do we even begin with something so elusive? How was it even discovered if it's practically invisible?
Well, that's the amazing part. Francium was actually the last element to be discovered in nature, not cooked up in a lab like so many others.
Really? That's fascinating. So it's out there, but barely.
It's out there, but it's playing a serious game of hide and seek. And it's not just about its rarity, it's also incredibly radioactive.
Ah, radioactivity. That explains the disappearing act.
Exactly. It's so unstable that its most stable isotope, francium-223, has a half-life of just 22 minutes.
Wait, just 22 minutes? That's incredibly short.
Right. I mean, imagine trying to study something that's constantly vanishing before your eyes.
That's like trying to build a sandcastle during high tide. So what happens during this half-life? Where does it go?
Well, it doesn't actually disappear into thin air. It decays into other elements.
Oh, I see. So it transforms.
Yeah, it transforms into astatine, radium, or radon. Poof. Like magic, but with a scientific explanation.
It's almost like it's playing a game of elemental hopscotch, jumping from one form to another. So even though it's naturally occurring, it's incredibly fleeting. I'm guessing no one has ever actually laid eyes on a bulk quantity of it.
You got it. It's like a ghost in the world of elements there, but not there. And this is where it gets even more intriguing.
More intriguing. Okay, you've got my attention.
Even though we haven't seen it in bulk, scientists have some pretty good ideas about what it might look like.
Really? How is that possible if we've never seen a substantial amount?
It all comes down to francium's place on the periodic table. It sits right below cesium in the alkali metal family.
Okay, I see where you're going with this. The periodic table is all about patterns, right?
Exactly. So, based on those patterns, scientists believe that if you could somehow gather enough francium, it would appear as a highly reactive metal.
A highly reactive metal, huh? Even more so than cesium, which is already pretty dramatic, right?
Oh, absolutely. Cesium reacts explosively with water. It's a classic demonstration in chemistry. But francium is predicted to be even more reactive.
Wow. It's amazing how we can predict things like that based on its position on the periodic table. It's almost like elemental fortune telling.
It's more like scientific detective work, really. And it gets even wilder. Francium was actually predicted before it was ever discovered.
Wait, predicted? How is that even possible?
Well, Dmitri Mendeleev, the mastermind behind the periodic table, had noticed these patterns in the properties of elements and their positions.
Right. I remember learning about Mendeleev in his periodic table. It's like a giant map of the elements.
Yeah, exactly. And just like a map can show you where undiscovered lands might be, Mendeleev's table predicted the existence of elements that hadn't been found yet.
So he was able to predict francium's existence and even some of its properties just by looking at the patterns in the periodic table. That's incredible.
It is. He even gave it a temporary name, ecocesium, meaning one below cesium.
So how did scientists go from predicting its existence to actually finding it? Did they just stumble upon it by chance?
It was a combination of brilliant deduction and meticulous observation. The discovery of francium is a testament to the power of paying attention to the smallest details.
Okay, I'm all ears. Tell me about this discovery.
So in 1939, a young chemist named Marguerite Perret was working at the Curie Institute in Paris.
The Curie Institute. Wasn't that where Marie Curie made her groundbreaking discoveries about radioactivity?
The very same. Perret was following in the footsteps of giants. She was meticulously purifying a sample of actinium-227 when she noticed something unusual.
What did she find? Was it like a giant flashing sign saying new element?
Not quite that dramatic, but equally significant. She observed some decay particles with surprisingly low energy levels. They just didn't match up with what she knew about actinium.
So she noticed a tiny anomaly, a detail that didn't quite fit. That's remarkable.
Exactly. It was that tiny discrepancy that set her on the path to discovering a brand new element. She meticulously ruled out all other possibilities. Could it be thorium, radium, lead? She went through the entire list.
Wow. Talk about a scientific detective. She didn't give up until she had exhausted every other option.
And that's how she finally arrived at the conclusion. She had stumbled upon element number 87, a brand new element.
That's incredible. And would she name this mysterious new element?
Well, initially she called it actinium K because it was a decay product of actinium. But later she chose a name that honored her home country, Francium.
Francium. It's amazing how even the names of elements can tell a story.
Absolutely. But finding it was just the beginning, right? The real challenge is studying something that practically disappears before you can even blink.
It's like trying to study a firework after it's already exploded. How do scientists even begin to work with something so fleeting?
That's where the ingenuity of science really shines. Because francium's natural lifespan is so short, scientists have to create it artificially.
Artificially. So they're essentially making francium on demand.
Exactly. They bombard other elements like thorium or radium with particles in a process called nuclear transmutation.
Nuclear transmutation, that sounds intense.
It is. But that's what it takes to create even the tiniest amounts of francium for study. And even then, they're working with minuscule quantities, often just a few atoms at a time.
So they're creating francium just to watch it disappear almost immediately. What kind of information can they possibly glean from such a fleeting existence?
You'd be surprised. Scientists have developed incredible techniques to study francium in those brief moments, and what they've learned is nothing short of remarkable.
Okay, now I'm really curious. What have they discovered about this ghostly element? What secrets has francium revealed?
That's what we'll delve into next. Get ready for more fascinating insights into the world of francium.
It's really mind-boggling, isn't it? We're talking about an element that's practically a ghost, and yet we've managed to learn so much about it.
It's a testament to the ingenuity and persistence of scientists, for sure. They're like detectives, piecing together clues from the tiniest traces of evidence.
And those clues have painted a pretty fascinating picture of francium, even if it is a bit blurry. We've talked about its predicted properties, its radioactive decay, and the challenges of studying it.
Right, we've covered a lot of ground, but there's one area we haven't really touched on yet. It's chemistry.
Ah, the heart of the matter. How does francium actually behave when it interacts with other elements? It's like trying to figure out the personality of a shadow.
A shadow with a very short attention span. But we can make some educated guesses, right? After all, francium belongs to the alkali metal family, and those are known for their dramatic reactions.
You bet. Think back to those explosive reactions of alkali metals with water. Well, francium is predicted to be even more reactive than its siblings like cesium and sodium.
Hold on, more reactive than those. I wouldn't want to be anywhere near that experiment. But I guess with francium's short half-life, any reaction would be more like a fleeting spark than a full-blown explosion.
Exactly. It's like a burst of chemical energy and then poof, gone in an instant. But even though we can't observe these reactions on a large scale, we can use what we know about the periodic table to predict how francium might behave.
So it's like we're using the periodic table as a guidebook, a sort of chemical roadmap to navigate the unknown territory of francium's reactions.
That's a great way to put it. And based on what we know about alkali metals, we can predict that francium would readily react with halogens like chlorine and fluorine to form salts.
Francium chloride, francium fluoride. It's fascinating to think about these fleeting compounds, these chemical whispers that exist for just a fraction of a second.
And speaking of whispers, there's one particular molecule that has caused quite a stir among chemists, cesium francium, or CSFR.
CSFR, huh? That sounds like a mouthful. What's so special about this particular combination?
Well, it has to do with a concept called electronegativity.
Electronegativity, right. That rings a bell from chemistry class, but it's been a while. Maybe you could give us a quick refresher.
Sure. Electronegativity is essentially a measure of how strongly an atom attracts electrons in a chemical bond. Think of it like a tug of war between atoms over those shared electrons.
Okay, that makes sense. So the higher the electronegativity, the stronger the pull on those electrons.
Exactly. And based on periodic trends, you'd expect cesium to be more electronegative than francium because it's higher up on the periodic table.
Right, so cesium should be the stronger puller in that electron tug of war.
That's what you'd think. But theoretical calculations suggest that in the CSFR molecule, francium might actually be the one with a slightly negative charge, meaning it's winning that tug of war.
Wait, really? That's unexpected. So francium, the element that's barely there, might actually be outmuscling cesium when it comes to attracting electrons.
It seems that way. Of course, these are just theoretical predictions. We need experimental data to confirm them.
I can imagine scientists are eager to test these predictions in the lab, but how do you even begin to study a molecule that contains one of the rarest and most unstable elements on Earth?
It's a challenge, that's for sure. But scientists are developing incredible techniques to trap and manipulate francium atoms, trying to coax them into forming molecules and observe their fleeting interactions.
It's like trying to choreograph a dance between two shadows. Speaking of cutting-edge techniques, I understand there's some exciting new developments in how scientists are studying francium, even with its incredibly short half-life.
You're right. One of the most promising areas is laser cooling and trapping.
Laser cooling and trapping, that sounds like something straight out of science fiction. How does that even work? And how does it help scientists study francium?
Imagine trying to study a hummingbird that's constantly flitting from flower to flower. At room temperature, atoms are zipping around like those hummingbirds, making them incredibly difficult to observe.
Okay, I get the analogy. So how do lasers come into play?
Lasers can be used to slow down atoms, cooling them to incredibly low temperatures, almost to absolute zero. It's like hitting the pause button on their movement.
Wow, so they're essentially creating a tiny, ultra-cold world where francium atoms are almost frozen in time, giving them a chance to study them in more detail.
Exactly. And when you can slow down those atoms, you can trap them using magnetic fields, creating a sort of atomic cage where you can observe their properties and interactions.
It's like creating a tiny, controlled universe where you can watch francium's fleeting existence in slow motion. What kind of things can they learn from these trapped atoms?
Oh, so much. They can measure their energy levels with incredible precision, study their magnetic properties, and even observe how they interact with other particles.
It's like opening a window into the quantum world, revealing the secrets of matter at its most fundamental level.
Exactly. And those secrets can have implications beyond just fundamental physics. There's growing interest in exploring francium's potential applications.
We've already talked about its potential in medicine. Are there other areas where its unique properties could be useful?
Researchers believe that francium's sensitivity to external fields, like magnetic fields, could make it valuable for developing new types of sensors and detectors.
Sensors and detectors, what kind of applications are we talking about?
Imagine sensors that could detect minute changes in magnetic fields, allowing us to monitor everything from geological activity deep within the Earth to the subtle signals of the human brain. Or detectors that could identify trace amounts of radioactive materials with applications in environmental monitoring and nuclear safety.
That's incredible. It's like francium, this fleeting ghost of an element, could help us unlock secrets hidden deep within the earth and even within our own bodies. It's amazing how something so rare and short-lived could have such far-reaching potential.
Absolutely. It's a reminder that even the most elusive phenomena in the universe can hold incredible possibilities, waiting to be discovered and harnessed.
This deep dive has been a real eye-opener. Francium has turned out to be far more than just a fleeting ghost on the periodic table.
It's a testament to the power of scientific curiosity, our drive to explore the unknown, and our relentless pursuit of knowledge. And who knows what other surprises francium might hold, waiting to be revealed by future generations of scientists. It's remarkable how much we can learn from something that barely exists, isn't it?
It really is. And it makes you wonder, are we done discovering elements? Is the periodic table like a finished book? Or are there more elements out there waiting to be found?
That's the big question, isn't it? I mean, the periodic table looks pretty full, but, there's always the chance, right? Especially when you think about those super heavy elements we talked about.
You mean even heavier than those? I can barely imagine. Where would they even be hiding?
Well, some scientists think they might be created in those like really extreme environments, supernovae or maybe neutron star collisions, places where matter is really put through the ringer.
Wow, so these undiscovered elements might be forged in the most extreme cosmic events. That's mind-blowing.
It is. And then there's the whole other side of things, creating them synthetically in labs, pushing the limits of what we can do.
So it's a two-pronged search, looking out into the vast universe and also pushing the boundaries of what we can create here on Earth.
Yeah, exactly. And it's not just about finding them. It's about what would their properties be? What could we learn from them?
It's like each new element opens a door to a whole new world of possibilities.
Exactly. I mean, think about uranium. Its discovery led to, well, nuclear energy.
Right. And silicon, the backbone of the digital age? It makes you wonder what kind of technological revolutions might be sparked by the discovery of new elements.
It's so exciting. It's like we're standing on the edge of a whole new era of scientific discovery.
And who knows? Maybe one of our listeners someday will be the one to make that next groundbreaking discovery.
Wouldn't that be amazing? To add a new element to the periodic table. What a legacy.
Well, I think it's safe to say that francium, even though it's, well, a bit of a ghost, has taught us a lot.
Oh, absolutely. About atomic structure, about radioactivity, even about potential uses in medicine.
It's a reminder that even the most fleeting, most elusive things in the universe can hold incredible secrets waiting to be uncovered.
And it's a testament to the power of human curiosity, to never stop questioning, never stop exploring.
Well said. It's been an incredible journey exploring the world of Francium with you today.
It really has. It's been a pleasure.
And to our listeners, thanks for joining us on this deep dive into the world of Francium.
Keep those minds curious, folks.
And until next time, keep exploring the amazing world of science.